This video is going to be about the common smart contract security vulnerabilities. So, first category is basic logic errors. This includes bad arithmetics. So, for example, not all ERC20 tokens have the same number of decimals. By default, they have 18 decimals, but there's examples like Tether and USDC where they only have 6. So, if you do math that doesn't take that into account, you're going to end up with a wildly incorrect value. Another thing is integer overflows and underflows. So if you're at the max value and you add 1, you'll overflow back to the lowest value, 0. And this is what it would be for an unsigned integer with 8 bits. An underflow is where you start at the minimum value and then you subtract 1 and you end up with the max value. So you can see that's an issue. If there's an ERC20 token and you send a small amount, even 1, and you have 0, if there's no integer overflow or underflow check in place, you can end up with just a stupidly high amount. Back in the day, people would have to use this OpenZeppelin safe math library up here, and then so using safe math for integer operations, and that was a way to add, subtract, divide, and multiply without risk of this kind of stuff happening. With Solidity version 0.8.0 and anything since then, the compiler automatically checks for underflow and overflow errors, so you don't need to use safe math anymore. Okay, reentrancy. So the infamous DAO hack was a good example of this. So this is an example of what it looked like. So there'd be a withdraw function with balances, and then it sends the value to the caller, and then decrements the amount in the mapping. This is bad because if the caller is a smart contract, the smart contract function that receives it could then call this again, and then it would send the same amount over and over and over again until you eventually have drained all the funds out of the wallet. And that's exactly what happened with the DAO hack. There's lots of ways to prevent this. So one way on this specific example is decrement the amount in the mapping first, then call. OpenZeppelin also has a reentrancy guard file, so you have this modifier called non-reentrant, and basically makes it impossible for a reentrancy thing to happen. On their token contracts, they also have safe transfer and safe transfer from functions, which should mitigate this as well. Uninitialized contracts. So the parity hack was kind of an example of this, where the library that one of the parity multisig wallets was using hadn't been initialized. When someone calls the initialize, it makes them the owner. And so the hacker, I mean, he was kind of just a goofball, but he called that, he became the owner, and then he was able to kill the contract from there. One way that this would happen is the constructor function used to be just the same name as the contract, and so you see the issue here. This is fall one out, this is fall out, this is from the Ethernaut game. And so the exploit that they want you to take advantage of here is that when this contract was deployed, it wasn't initialized because this is not the constructor function. So then when you call this function, it sets you as the owner, and then you can do whatever you need to if you're the owner. Nowadays, there's a constructor keyword, so that eliminates the likelihood of this occurring. Access control. So by default, functions the visibility is set to public, which is not always desirable. So this is something I coded up in Remix real quick. So you could add funds to this contract if you were the owner and then withdraw it later. You could treat it like a vault or a wallet. And when you initially deploy it in the beginning, it'll set you to the owner, assuming you put your wallet address in here. But the problem is the change owner function is public. So any random person could call this, become the owner, and then withdraw my funds from it to their own account. So you got to be careful which functions are set to whatever, and make sure that you have correct modifiers. It's like there's an only owner modifier on withdrawal, if that makes sense. Maybe this change owner should have that as well. On a similar vein, authentication with tx.origin as opposed to msg.sender can be very bad. So what is the difference between those two? Basically, tx.origin is the externally owned account, so the user that initially did whatever chain of contracts. So here, for example, this is the EOA, and this is an intermediary contract, and this is a contract that actually wants to be interacted with. So message.sender is contract A. tx.origin is always this. You could have 15 contracts in sequence. That would be crazy, but the tx.origin will always be the account. So then what some people think is, well, maybe that's a way you can mitigate against reentrancy, because if it's tx.origin matches the msg.sender, then clearly it can't be a smart contract, and so it can't use reentrancy. But again, that's not true because of this right here. So it's a terrible way to validate against reentrancy. And in general, just avoid tx.origin. Occasionally you run into an incorrect implementation of the ERC standards. So as a very common example of this is there's some ERC20 tokens where their transfer function does not return a Boolean value. So Tether and Binance Coin being the biggest ones, but there's others as well. And so if you have functionality within your contract and you make assumptions that the ERC20 token, for the transfer function specifically, is going to return a Boolean, you can get some weird functionality because some of these contracts don't return that. Could also have a case of just the incorrect interface implementation. So if you misspell function names or the logic within the functions of the implementation itself are false. So for example, ERC20 tokens need to have a balance of function that takes an address as a parameter and then returns the value of the number of tokens it has. If the balance of function that you code up doesn't do that, then it's not meeting the standard. Oracle manipulation. So certain decentralized finance applications and whatnot need off-chain data, and oracles are the bridge between the on-chain code and logic and then the off-chain data. But that being said, they're prone to freeloading, Sybil attacks, mirroring, all sorts of interesting issues. Bad randomness. So there's no such thing as true randomness on chain. If you have a game that needs to roll dice or flip a coin or generate random numbers, you can't use on-chain data to get that randomness, because wherever the source you're pulling it from, some user can pull it from that same source and use that to manipulate values, and I'll show you an example of that later. There's workarounds for this. So one of them is the chain length VRF, which is a provably fair and verifiable random number generator. DOS, denial of service. So the parity hack, I guess you could consider this. So like I mentioned earlier, he became the owner of one of the libraries that the multisig wallet was using, and then he called the kill function, and the kill function destroyed the library and in effect the entire wallet. And so self-destructed everything. $300 million worth of Ethereum and funds just gone. So any kind of freezing of funds or wallets or self-destructing contracts, that's a DOS. Griefing, this isn't as common, but anytime you can clog up the network to make it unusable for others, that'd be griefing. Now usually it's not economical because of how expensive gas is, especially these days, but there could be scenarios. So complex logic errors. I'll show you some examples of this where there's a flawed logic in the contract execution flow itself. It's hard to make a base case scenario for this to happen because it varies between each application. And this is where all those unforeseen attack vectors come in. And then this also gets into the question of a bug versus an exploit. So a bug is like when the developers are coding up a contract and it has to do X, Y, Z, and the code is not correct. It doesn't quite do that. An exploit would be the code matches the specifications, but there's some vulnerability in the architecture that allows stuff to happen. So the Beanstalk DAO, for instance. So this hacker took out a huge flash loan, hundreds of thousands of dollars, and got governance tokens in the Beanstalk DAO, and then he used his majority of governance tokens in the DAO to approve sending the funds from that DAO to his own private wallet. Now, that's not a bug. This worked as intended. If you have the majority of governance tokens, you're allowed to vote on proposals like that. The problem is the Beanstalk DAO developers didn't foresee someone taking advantage of flash loans to manipulate the governance like that. And there's other miscellaneous vulnerabilities as well. So some funky stuff can happen with delegate call. So when you call a contract and that contract calls another contract, the msg.sender and value are updated each call. Delegate call allows you to essentially tunnel through it and keep the sender and value the same. If you use an outdated Solidity compiler version, you can get funny versions. Also, when you're in the initial stages of development or you're using libraries, floating pragmas are fine, but once you're ready to deploy and when you're testing, you want to use a specific Solidity version, so there's no funny behavior with the compiler. Minor exploits can happen. You don't see this a whole lot, but they can order the transactions differently within a few seconds of when they get it, or manipulate the timestamp slightly. Again, that's not going to be a huge issue if it's a time lock in some application for days or months or years, but if a few second difference does matter, then there's an exploit there. And of course, more is being discovered all the time as the Web3 space matures. This space is still in its infancy, so there's no doubt that we're going to see millions and even billions of dollars of more hacks and exploits and vulnerabilities, but that's what it's got to take for the space to grow. Okay, this is an example of the power of integer underflows. So this is in the Ethernaut game. This is the level token. So here's their ERC20 token, the balances mapping, total supply, blah, 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 blah. We initialize it. You can see balance of player, which is me. 20. I've got 20 tokens. So now what I'm going to do is I'm going to transfer to the contract itself 21 tokens. So a contract has the 21 that I sent it. And now I've got a stupidly high number of tokens, which is what you need to do to pass the level. You should end up with more than 20 tokens. And sure enough, that was all it took. So this was when it talks about opens up on the safe math library. We don't need to do this anymore with Pragma Solidity version 0.8.0 and more recent. So this is the fallout level that we saw in this in the PowerPoint. So this is what's supposed to be the constructor function, but again, it's misspelled, so it doesn't actually get initialized. The owner should be the 0 address once you get this instance back. Once you're the owner, that's when you can collect the allocations and, drain the wallet of its funds, which is the goal of this thing. Claim ownership of the contract, and you complete this level. So, contract owner 0 address, so it has not been initialized. So now all we got to do is call this function and set ourselves to the owner. There's my address. So now I can do anything that this only owner modifier is on. That was the goal level, just claim ownership. So now that we're the owner, we can pass the level. So another level of Ethernaut. This is CoinFlip. So it does some math to figure out if it's a heads or tails, and then basically you have to guess true or false, and then it'll return yes or no. And the goal of this level is to get it correct 10 times in a row, which mathematically, if it's random, is going to take forever. But because it's using on-chain data, it's not exactly random, and there's a way to exploit that. And this is how it's done. So I've copied the contract over here into Remix, import the safe math library, and here's my attack contract. So it imports the CoinFlip and then does the same map. So it sets the victim to something we set in the constructor, and then it's going to flip. So it's going to calculate the exact same value that this function is going to calculate. And then once it has that value, that is what it'll input for the guess, meaning it's going to be right every single time. So all we have to do is deploy this and then call it 10 different times. So here's the address of the CoinFlip. Our victim. So consecutive wins is public, so we can see how many this is. And right now it is 0. So obviously we haven't guessed anything yet. Okay, so now what we're going to do is flip. Call this again. 1. We got 1 win. Call it again. Now we're at 2. So I'm going to repeat this process 8 more times, and that should allow us to win the level. Okay, so now we're at 9. This should be the last flip, assuming that it doesn't get canceled or reverts. Okay. One last time to check. We got 10, which is the goal of this level. There it is. Okay, another Ethernaut level telephone. The goal of this one is to exploit the tx.origin and msg.sender discrepancy. So here's the telephone address. So I've copied the telephone contract into Remix, and the attack is very simple. So we're going to set the telephone address to what it is, and then the attack is just going to call change owner. And then you could set any address into here. Well, actually, no, you have to claim ownership. So you have to send your wallet in here. So message.sender. And so what this does, what this contract does, is it calls change owner on this. tx.origin is my wallet. Message.sender is this contract, which we'll see the thing for in just a sec. Maybe we'll see it. Who knows? There it is. Okay. So this address right here, whatever it ends up being, yeah, that's going to be the message.sender here. The tx.origin is going to be us. And the owner that we're passing in, that'll also be us. And so then, because this is true, it'll set us to the owner. All right, attack. And there's our address. We win. All right, here's an example of bad access control. So we will deploy this using this 5v3 wallet. And we'll set ourselves to the owner. Actually, you know what? I need to deposit some Ether in there. Okay, we'll deposit 25 Ethereum. Okay, so that's a sizable amount of money in here. Now, so if we wanted to withdraw, say, 2, we could do that. Oh, this isn't way. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Transact. There. Now we pulled out 2-way. Okay. So, but now let's say I was this wallet here. And I called change owner and I set myself to the address. Now I can withdraw 2 Ethereum. If we go back to this guy can't withdraw anymore because he's not the owner. Now, I mean, yes, you could say, well, he can just change owner again, I guess. But if this were a real attack, this guy would just drain everything. Bam, now there's 0. Now look at how much Ethereum this wallet has. Pwned.